Hey guys, Mr. Parkins here, or as Josh likes to overdo, Mr. P. It is currently E-Block on Thursday, and I am just hoping nobody comes in my classroom as I'm doing this to throw me off, so we'll give it a shot. Alright, so section today is on hyperbolas. Now, hyperbolas are definitely something I don't think you've seen before. First, we'll just go with what they look like. So examples over here on the right. An example of a hyperbola would be like this. That's the left portion of it, and this would be the right portion of it. So they do kind of look, that together right there is one hyperbola. You can also have what I call a top-bottom hyperbola. I'll do a different color for that one. So a top-bottom hyperbola would kind of look like this. Top half, bottom half. Okay, and they are symmetrical. So we'll see how those are going to come out, but that's basically what they're going to look like. Okay, now the first thing we want to look at is the equations and how they differ from the other things that we have done. The only big difference, if you look at them, they look a lot like the ellipse equations, but the only difference is the sign in between them. All right, if you remember ellipses, we had pluses in between the two terms there. Now we're just going to have a minus. That's the only difference between the equation of a hyperbola and an ellipse. Okay, the other main difference to look at is when do we have a horizontal, or what I would call a left-right hyperbola, and when do we have a top-bottom or vertical hyperbola, and that has to do with what comes first. Okay, so if you look at the equations there, in this one the x is what comes first, and then in the vertical ones we have the y coming first. Okay, so that we're just going to have to look at which term it is that comes first. That'll tell us if it's a top-bottom or a left-right. Okay, next things to look at are the center. Again, it's the H and K shifts. That should be very simple for you guys. The foci, slightly different equation with the foci. So if you look at what we have there, this is going to be c equals a squared plus b squared. Now that basically is the Pythagorean theorem, all right? And we'll talk in class tomorrow about why it's different. It has to do with where the foci lie, okay, where the foci are when we do these out. So we'll take a look at that. Now vertices, again, are just going to kind of come out from the formula. And asymptotes, I'll tell you what, I wouldn't even worry about the asymptotes here, okay? We're going to graph them. I'm never going to ask you to just give me the asymptotes. So that'll happen from our graphs, okay? So let's take a look at some examples now. Okay, so going on to example 1. What we have here is, if you look at the equation, obviously we're not going to have any shifts, okay? So our center is going to be at 0, 0. Okay, so I like to graph that first and just plot a point. Now, the shifting is really the exact same thing as an ellipse. In the first part of this problem, you're going to think I'm actually doing the same things that we were doing the other day with graphing the ellipse. So if we look underneath the x, we see a 4. We're always going to do the square root of that, so 2. That's going to be our shifts left and right. So from my center point, I get a point there at 2, 0, and I get a point at negative 2, 0. Alright, same deal with the y. Underneath the y is 16, so we think about the square root of that being 4. I go up 4 and down 4. Okay, so those are the points that we're starting off with. Okay, now if it was an ellipse, we'd be done, right? We'd basically just connect those points and have the ellipse that we're looking for. So here's the difference with the hyperbola, and this is just the way to do it, all right? Using those 4 points, we basically draw a rectangle, but we're going to do a dashed rectangle because it's not technically part of the hyperbola. All right, so I'm going to do this in green here as best I can. I'm just drawing a dashed rectangle, okay, with those points being the outline. Okay, so that's the first step. Now what we do is we draw the diagonals of that rectangle. Okay, so if I draw the diagonal and extend it through, this is what one of the diagonals would look like. Okay, and then we do the same thing with the other diagonal. Okay, remember the asymptote stuff that we crossed out up top in that chart? These are the asymptotes. This is basically where the hyperbola is going to get closer and closer to, but never actually touch. Okay, so now we're ready to graph the hyperbola. Thing we have to look at right now is which term is first, okay, and we have the x term first. Like I said up top, that tells me that this is going to be a left-right hyperbola, okay, so that's kind of something that you might just want to make a note of. It's a left-right hyperbola because, again, the x squared term is first, okay. So now we're ready to graph it. What the hyperbola is going to do, I'll graph the hyperbola in black. Actually, let's do it in red. So it's going to go through that point there, and it's going to go through that point there, okay, because those are the points that we drew at the beginning based off of the square roots. All right, and now from there, it's just going to basically go up and down from that and go along closer and closer to the asymptotes. Okay, so that's how we know what the shape is going to be. If you can picture that box looking differently, that's going to maybe give us a more well, that was terrible. Let's try that again. That's going to give us a more narrow hyperbola or a wider one or anything like that. Okay, so that's basically the graph. 90% of the time, that's what we're going to be doing there, is just drawing our graph. Okay, now the vertices are those points that, those red points that I made there that just get a little bit bigger, so let's just state those. So that's at 2, 0, and negative 2, 0. Okay, and then the final thing is to calculate the foci. Alright, so let's just check that out real quick. In calculating the foci, we're just going to use that formula that was up above, that c equals the square root of a squared plus b squared. So what we have is c equals the square root of, now the a squared was 16, the b squared was 4, so c is the square root of 20. Alright, now if you estimate the square root of 20, that's about 4.5 approximately. The foci are going to be, I'll zoom back into the graph, again about 4.5 from the center, so 1, 2, 3, 4.5. That right there is a focus point. Okay, and then over there on the left, those are where your focus points are. So these are outside of the ellipse, but it's in a similar spot to what we had for parabolas, if you think back to that. Alright, so the foci, if we state those, would be, let's do this a little fancy, this would be plus or minus the square root of 20. Actually, I should rationalize square root of 20. That would be 4 times 5, which is 2 radical 5, right? So that would be plus or minus 2 radical 5, comma, 0. Okay, and there's that full example right there. Alright, let's check out example 3 now, which is going to be the same concept, but now we're going to have a shift involved. Okay, so basically what we're looking at here, we've looked at this with the ellipses. I'd like to put that over 1. Let's do the center first. Now be careful with where the y and the x are. Okay, the x squared, the x term is the second term now. So if I'm going to be dealing with my center, I'm going to be looking at the x plus 2. All right, so my center is at negative 2, positive 3. All right, real common mistake there to call it 3, negative 2 if you're not careful about where the x and y are. All right, so there's my center. Now we'll just graph that point. Negative 2, 3 is up there. Now we go with the square roots, and again, underneath the y is the 1, so that's going to be a stretch up and down 1 with my y. Okay, so I'm going up 1, down 1 like that. Okay, under the x is a 9, so we go square root of that is 3. 1, 2, 3 to the right, 1, 2, 3 to the left. All right, so there's the points that are going to outline our box. All right, so let's draw that rectangle now. Okay, dashed lines because it's not technically part of our graph. So that's what our rectangle looks like. Now we go with the diagonals. All right, so a little trickier on this one just because it's pretty narrow. Okay, so that would be one of your diagonals. The other one, obviously use a ruler if you have it available, but that's what we're looking at there pretty much. Okay, so there's our diagonals. Now we're going to look at which term is first. Okay, so we have in this case the y term being first. And so since the y is first, that's going to be a top-bottom. Okay, so top-bottom hyperbola here. So that tells me, now let's graph it in red, that this point here is going to be one of my vertices, and then the point below it will be the other vertice, or vertex. Okay, so there we go. Now this is going to be a very, very wide hyperbola, right? So if you check this out here, just go close to those asymptotes, it's going to come very wide. Alright, same thing over on the left. You're bound to screw up one of these 4, probably like I did. Alright, and that's kind of what it's going to look like. Just for the heck of it, if this was the x term being first, it would be a really narrow hyperbola, so I'm just going to draw this in blue and then get rid of it because it's the wrong answer, but this is what that hyperbola would kind of look like. Alright, if you can picture that. It's not a V, I know, without being able to be really careful. Alright, that's what it would look like if the x term was first instead of the y. Alright, so I'll get rid of that now so you don't think that's part of it. Okay, so that's basically what the graph looks like right there. Alright, so now our vertices are again going to be those 2 red points that we started off with. So what we're looking at there is negative 2, 2, and then the other vertex is negative 2, 4. Okay, and again, just doing out the little math for the foci. Let's see what we come up with. This is going to be c equals the square root of, I lost it. Sorry if I'm making you dizzy with this. 9 minus 1, so that's going to be square root of 8, which is going to be, if we rationalize it, 2 radical 2. Okay, now the focus points here are going to be above and below the hyperbola, okay, because they have to be basically towards the curvature of it. So if we look at that, again, square root of 8 is a little less than 3. So from my top point there, I'm going to go up 1, 2, a little less than 3 would be right about there. So in black I have that focus point, and again 1, 2, a little bit less than 3 would be that point down there. All right. X coordinate is the same for both of those. X coordinate is -2. All right. Now we saw this the other day with the ellipses with the focus points. What we have to say here for the y value starts at 3, and then we add or subtract that 2 radical 2. All right, so that would be a nice concise way of giving those focus points. Okay, one quick note before we move on to the other pages here. If we go back up a little bit to this little note here, transverse axis and conjugate axis. Okay, so what we have here, just a quick thing, the transverse axis is a segment whose endpoints are the vertices of the hyperbola. Okay, so I'm going to just draw that on this example that we have over on the right. The transverse axis would be the vertices, so if we look at this here, so I should probably zoom in, let's check that. Alright, that right there would be the transverse axis. Okay, and then the conjugate axis would be the other one. So basically that's going to tell you, if we have some information about a harder problem, if it's going to be a top-bottom or if it's going to be a left-right. Okay, and again, just looking at this one here, this would be the transverse axis in this case. Okay, so that's going to help us on the next problem that we check out. Okay, I promise I'm really being careful on the time here, and I know I'm already over 10 minutes. So on page 2 here, I'm actually going to skip all of page 2. The only difference here, this is the completing the square. Okay, so we did a lot with that the last couple of classes. So basically on all of these, you'd have to complete the square and go from there. If you guys could just, if you have some time, just try out number 2 for class tomorrow, okay? And then we'll work through the other ones in class, all right? I want to take a look at one more problem, and we're going to do that from page 3. Okay, so we're going to do out example 1 on the back here, all right? And this is going to give us a little bit of information, and we have to go from there, come up with the equation, okay? But again, like we've been doing, I think we should graph it first and come up with the equation from the graph, okay? So here we go, vertices at -5, 0, and 5, 0. So I'll sketch a little axis over here and draw, again, rough sketch of what we have. So vertices at -5, 0, and at 5, 0. Now, if those are the vertices, that tells me immediately that I know it's going to be a left-right hyperbola. Okay, so let's try to get some information from that left-right hyperbola. So therefore, if we come over here and kind of outline our equation, remember there's got to be a minus in between there. Okay, these are both squared. The right side has to be 1. Pretty easy to know if it's a left-right, that means my x term has to come first. All right, so we got an x there and we got a y there. Good. Now, the other thing, I probably should have been a little smarter than that. If it's at -5, 0, and 5, 0, our center is going to have to be here at 0, 0, right? So really, we don't need the set of parentheses up top. It's just going to be x squared in the numerator of the first part and y squared in the numerator of the second part. Okay, so sorry. You can leave it as is. If you just put, actually, let me go back to that. You could just leave it and do a -0, all right? But that's kind of childish, so I'm just going to erase what I have there. My numerator is just going to be x squared, my denominator is going to be y squared. Okay, so let's check that. So numerator here, x squared minus y squared equals 1. Okay, so all we got to figure out now is what's going on with our denominators. Okay, well in the x direction, you can tell from the vertices that we're stretching left and right 5. So underneath the x is just going to be that 5 squared, all right, or 25. So straightforward on that one. Now, in order to figure out what we're doing in the y direction, we have to take a look at the second piece of information that we haven't seen yet, which is this conjugate axis. Okay, so we have a conjugate axis of length 12. We just discussed before what the transverse axis was. That's already kind of drawn for us. So the conjugate axis is just going to be the one that's perpendicular to that. All right, so in general, the conjugate axis would be the axis in this problem going vertically. All right, so all we have to figure out is how long that is, which is pretty simple since they tell us that it's length 12. All right, so what we're going to do with that, if it's a length 12, I know that I have a point that's going to be up 6 and down 6. All right, and again, if you're just stretching, if this distance here is 6, that's just going to give us 6 squared underneath there, or 36. All right, so there we go. That's going to be the equation. We don't have to graph the whole thing, so if you're not asked to graph it, don't. That's our final answer right there. Okay, so I know I said that was the last example, but I lied. Just want to show you guys one more difficult one before we see each other tomorrow. So example 4, let's check that guy out. I'm going to go through this kind of quick, so if I lose you, no big deal. But I just want you to see this out. So real quick, I'm just going to graph the vertices approximately, -4, 1, and -4, 9. All right. From those vertices, you want to figure out your center from there. So in blue, the center would be exactly halfway between that. Which would give us the center at -4, 5. Okay, so that's where our center point is going to be. Now, what we have to do from there is figure out basically what the horizontal stretch is going to be from the center, and that's where we're going to have to use that little ABC equation. Okay, so let's come to that. C is going to be the square root of a squared plus b squared. All right, and what we're going to look at to help us get to C is we're going to look at this guy here. All right, if you think about that 5 plus or minus the square root of 97, that's the square root of 97 is actually what your C value is. Okay, so we're going to plug square root of 97 in for C. All right, our A value, looking over here at the graph, is going to be the distance from the center up to that vertex point squared. So that's a length 4. So inside our square root, we're going to have 16. All right, 4 squared, and then we're basically solving for our B value. All right, like this. Okay, now in squaring both sides, we end up getting that 97 equals, the square root goes away, so it's 16 plus b squared. Subtract the 16 over, that gives us a nice 81 equals b squared, which square rooting gives us that b is 9. All right, so that's pretty much everything that we need to figure out what the equation is. Okay, so now we're ready to write our equation, and I'm just going to go a little lower here. I know I'm going into example 5 kind of, but we'll be alright. So our equation, if we outline it here like we've been doing, we have that as the first part. Second part, we know it's equals 1 over on the right side. So because this is a top-bottom, now we know it's a top-bottom because the vertices are up here and down here. Okay, so we have that part. So we know that the y term has to be first, okay, x term is second. Now we take into account the center, okay, so the center, the y value is 5, the x value is -4. Alright, so that's what gets filled in there. And then our stretch in the y direction was 16, and the stretch in the x direction is what we found out from the ABC equation, which was 9, so 81 is going to go down here. There is our final equation, and that's it for today. See you guys tomorrow.